Hi guys! Today we're going to talk about Chapter 10, which deals with gas laws. So as always in your study guide, you're going to find your learning objectives. Make sure that you read over those before a test. And we're going to start with the 4 variables that you could measure for a gas. So if you have a gas, there are 4 things that you could measure for it, which are volume, temperature, number of particles, and pressure. So let's talk about each of those. We'll start with volume. So volume gets a symbol capital V, and you can use any kind of units for the volume. Typically the most popular is liters. You can use milliliters, kiloliters, microliters. You could use centimeters cubed, meters cubed, decimeters cubed. You could use gallons, cups, all kinds of stuff. For temperature, it's capital T, and remember temperature is related to the average kinetic energy. So it has to do with the motion of the particles. And for this chapter, the only units of temperature that we can use are kelvins. So if you are given Celsius or even Fahrenheit, you'd have to convert it to Kelvin before you move on with any calculation in this chapter. Number of particles is lowercase n, and the units, of course, are going to be moles. And then pressure is capital P, and pressure, if you remember, is due to collision of gas particles. It's the force per unit area, and it is caused by collisions of gas particles with the walls of the container. Just double O. So when those gas particles hit the walls of the container, that's what causes pressure, is collisions of gas particles. There are many, many units of pressure. So at sea level, standard pressure, 1 atmosphere is the standard. And they came up with that unit of atmospheres just so that they can have a number that's very easy to use. And so 1 would be like standard. That is equivalent to 760 millimeters of mercury. And where this comes from, if you remember from last year, so back in the day when we'd make a barometer, we'd take a tub full of mercury, and then we'd take a, it's called a eudiometer. It's a really long graduated cylinder, basically. And we fill it with mercury, put our hand over it, and then flip it upside down real quick. So I'm going to try to draw that like this right here. So this is closed. And when you do that, most of the mercury stays in. So this is still mercury here. But some of it leaves, right? Goes out. And the reason why that happens is because you have gas particles here that are pushing down. But then you also have gas particles here that are colliding and pushing down on the liquid here. And so it keeps this liquid in the tube here. So I'm going to go ahead and color it here. So there's your mercury. This is all mercury here. Okay. So if you are at sea level where there's standard pressure, the height of this tube, or is the height of the mercury, I should say, in this tube is 76 centimeters, which is the same thing as 760 millimeters. And so that's where the 760 millimeters of mercury comes from. If there is a lot more collisions, lots more pressure, then that pushes that liquid to a higher level. So that number is higher than 760 millimeters of mercury. If there's not as much pressure, so there's not as many collisions, and there's less pushing on that liquid, and so the liquid falls down to a lower height. And so that's where that comes from. Torr is the same as a millimeter of mercury. This is just named after a scientist to honor him. And 101.3 kPa, that is also equivalent to standard pressure. Kilopascals, this is the same Pascal that made the Pascal triangle, so again, they wanted to honor him and name a unit after him. It is also equivalent to 14.7 pounds per square inch. So if you were to draw a square inch like this, there are 14.7 pounds pushing on each square inch of any of you or of any material, any piece of matter. The air particles are pushing on it with almost 15 pounds of pressure for every square inch. You do not need to know this one, but you probably want to know these to be able to convert between the two. So the next thing we're going to talk about is these laws that we studied last year that relate between these four variables. And so each of these laws, we are going to hold two of those four variables constant and look at the relationship between the two. Just something to keep in mind that the AP exam is going away from memorization, so you do not need to know the name of the law, but you do need to be able to understand and explain the relationship between the variables. Note also that these relationships only apply if the other two variables are held constant. So when you compare pressure and volume, for example, that's only if temperature and amount are held constant. I see a lot of people on the test that will tell me, oh, because temperature is higher, that means the volume is higher, and because the volume is higher, the pressure is lower. You cannot do that. You can only relate two variables at a time, because that relationship only applies if the other two are constant. So if the temperature is increasing and the volume is increasing, that means the pressure has to be held constant. If the pressure is not held constant, then that relationship between the pressure and between the volume and the temperature is no longer true. So let's look at the first one, which is Boyles Law. So Boyles Law looks at the relationship between the volume and the pressure of a gas when the amount and temperature are held constant. So at constant amount and temperature, the pressure of a gas is inversely proportional to its volume. And that kind of makes sense. So if you have a, like last year we did the Boyles Law lab where there was a syringe and we filled it up with air, we closed it, and then we would push to decrease the volume, and it would get harder and harder to push because the pressure was increasing. So it's an inverse relationship. You need to know it in words like this. You also need to know it in terms of like a mathematical equation. So pressure, we said, was inversely related to volume. So we can say it's proportional to 1 over V because it's an inverse relationship. We can remove the proportionality symbol and put an equal and a constant. So we can say that P is equal to a constant, let's call it B. It's 1 over V. And so if you rearrange this, you get P times V is equal to a constant. If you have changing conditions, so if I have a gas and I measure its pressure, let's call that P1, and I measure its volume, V1, multiply them together, I get this constant. Let's say I change the pressure, so now it's a new pressure. The volume will also change. If I multiply those together, I should still get the same constant, as long as it's the same gas at the same constant amount and temperature. So I can set both of these equal to each other and say that P1 V1 is equal to P2 V2, and I can use that for changing conditions. The last thing you need to know is if you were to graph these two variables, what would that graph look like? So at constant amount and temperature, if I were to graph volume versus pressure, it is an inverse relationship, so it kind of looks like this. Let's look at Charles' law. So Charles' law, you keep the amount and the pressure constant, and you look at the volume and the temperature relationship. If you remember last year, we put some ivory soap in the microwave. The ivory soap had some pockets of gas in it, pockets of air, and so when we heated it up, increased the temperature, it took up more volume. The soap, kind of grew bigger, right? And so this is a direct relationship. So the volume of gas is directly proportional to its Kelvin temperature. So we're saying, oops, not pressure. We're saying that volume is proportional to the temperature. So we can say volume is equal to a constant, let's call that C for Charles, times the temperature. So if we rearrange this, V over T is equal to a constant. If we have changing conditions, so we can measure the volume and the temperature of the gas, divide them together, you get a constant. If we change the conditions and we have a new volume and a new temperature and divide those, you get that constant, so we can set those equal to each other if we have changing conditions. And then graphically, if we were to graph the volume versus the temperature, we would get a straight line like this. And excuse me, if this was the Kelvin temperature, then we would meet at the origin there, because at 0 Kelvin you wouldn't have any gas, so it wouldn't have any volume because you don't have gases. Everything would freeze, everything would be a solid. If this was the Celsius temperature, then we would have this hit at the intercept of negative 273 Celsius, which is 0 Kelvin. Gay-Lussac's law is next. Remember that one we did last year as the can crush demo? So at constant amount and volume, the pressure of a gas is directly related to its pressure. If you increase the temperature, that means particles are moving faster, so they're going to collide more, as long as you're holding the volume constant. So mathematically, if we look at the pressure, it is proportional to the temperature. So we can remove the proportionality symbol and put an equal with a constant. We're going to call that G for Gay-Lussac, times the temperature. If you rearrange this, you would get P over T is equal to a constant. And just like before, if you have one set of conditions, divide those to get the constant. You change the conditions. You have a new pressure and a new temperature, divide those, you get a constant, and so those can be set equal to each other if you have changing conditions. If you plot pressure versus temperature, you would get a straight line, and again it would hit in the origin if this was the Kelvin temperature. It would hit at negative 273 Celsius if this was the Celsius temperature. And that's one of the ways, those two are some of the ways that they calculated what absolute zero would be, is by looking at that intercept. Avogadro's law is next, and Avogadro's law looks at constant temperature and pressure. When you change the volume, how does the amount change? So obviously if you have more gas particles, they're going to occupy more volume, and so that is a direct relationship. And so V is proportional to N. So V is equal to a constant times N. So V over N are equal to a constant. If we have changing conditions, then V1 over N1 is equal to V2 over N2. And if you graph that, you'd get a straight line. Obviously, if you have no moles of gas, you'd have no volume, and so they do hit in the origin. You can also use Avogadro's law. So you can use it if you have just one gas where you change the conditions, but you can also use it in the stoichiometry of a reaction of gaseous species. So if I have, the volume of a certain gas, so like let's say I have H2 plus N2 yields ammonia, and 3, 1, 2. So I could say that, I need 3 liters so if I have, let's say, like 2 liters of hydrogen, I want to know how many liters of the nitrogen I need to react with it. That's 2 here. What I could do is I could use this, with 1 being the hydrogen, for example, and 2 being the nitrogen. So I could say 2 liters of hydrogen, and I have 3 moles, is equal to X liters of nitrogen, and I have 1 mole. So I could use that to actually go from one gaseous species to another in a chemical reaction. All right, so from all these laws, I can come up with the ideal gas law and the combined gas law as well. If I have, so let's say you have Boyles Law, which is P times V is equal to K, right? And I want to combine with it, let's say Charles Law. So Charles Law says V over T is equal to K. So I can do V over T is equal to K. Let's do Gay-Lussac's law. So Gay-Lussac's P over T is equal to K. And then Avogadro's V over N is equal to K. So I kind of combined all of them into this. Something magical happens when you combine all of them, and instead of, whatever this is, it becomes R, which is the ideal gas law constant. So the ideal gas law is PV equals nRT, Judah. If I wanted to know what R is, so that is given to you on the green sheet in one set of units. But let's say you're stuck for some reason and you want to find out what R is. If you look at STP, STP, 1 mole of a gas has a volume of 22.4 liters. And STP means temperature is 273 Kelvin, and the pressure is either 1 atm or 101.3 kPa or 760 millimeters of mercury, right? So what I could do is I could solve for R. I could say R is equal to PV over NT and plug these values in. So let's say I want R in kPa times liters per mole Kelvin. So I would plug in the kPa, the 101.3, the volume of 22.4 liters, the N is 1 mole, and the temperature is 273 Kelvin, and I can find out what R is. So let's have these in our notes. So R would be 0.0821 atms times liters per mole Kelvin, or 8.31 kPa times liters per mole Kelvin, or 62.4 millimeters of mercury times liters per mole Kelvin. So these are all the values of R that you would need. I believe on the green sheet, the one with the ATMs is there. So that's called the ideal gas law. The combined gas law is if you have one set of conditions, so I'm going to rewrite, R is equal to PV over NT here. So let's say I have a certain gas, has a certain pressure, certain volume, certain amount, certain temperature. If I do this calculation, I get R. Let's say I have completely different gas, or I take that gas and change things in it or something like that. Well, the new pressure, the new volume, the new amount, and the new temperature, if I calculate this, I also get R. So I could set those kind of equal to each other because they're equal to R. So I could say P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And that is called the combined gas law. I could use it if I have one gas where I'm changing conditions, or I could use it to relate two completely different gases. That still works. And so now that I know the ideal gas law, I don't need to memorize the relationship between any of these anymore. Because what I could do is if I know PV equals nRT and I rearrange it to solve for R, and I write this with ones and then equal, and then this again with twos, then I get this. And then I could cancel out whatever is constant. So I'm going to rewrite this here. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Let's say I want to know what the relationship is between pressure and volume. So I can only look at that relationship if amount and temperature are the same. right, are constant. So if the moles are constant and they're on both sides, I can cross those out. And if temperature is constant, I can cross it out. So I get P1V1 equals P2V2, which is Boyles Law. So I could do that with any two variables where I cross out two variables and I get the relationship between the other two variables. And that gives me the relationship between any of those two variables, which is those four laws. So I no longer ever use these. I just use the combined gas law, this one, and I cross out whatever is constant. You want to use the ideal gas law if you don't have changing conditions. So you have one gas at one set of conditions, one pressure, one volume, one amount, one temperature. You want to use this one if you are changing the conditions of that gas, like changing the pressure or changing the volume or something like that. Or if you're comparing two different gases to each other.